Mike, thank you. That was real material to chew on, and I will be going through that whole thing again. Now, yeah. So you did mention you wanted to go through the gyroscopes and present on that, if you're open to it.
Yeah, well, you requested it, so it's about a 20 minutes, so I can go through it pretty quick. It's not as heavy duty as this last one.
Like sir, I said, I would be honored to have you go through
the second part of the gravity presentation deals with Maxwell's equations, where you move it all over to electromagnetic field. If you want that one presented sometime, we can do it also, but this one's fairly quick and easy. To start with here, this is more of a picture history of the Boeing work, and it contains mainly pictures rather than verbiage in that. And so I had a lot of trouble getting it through the Boeing release system, because the IP guys went through it with a fine-tooth comb, because they're saying pictures contain more data, like 1,000 words. So they went through it. I had to send this one through twice to get it out. It was originally presented at COF 7 there, Tom Vallone. Matter of fact, this is what got him interested in having me build the little tabletop demo model that I showed you last time. Okay, this presentation, it's mainly non-technical pictures of Boeing CMG work. It started back in the 60s, it continued on into the 90s. I got involved with it in 1995 when I took over lab operations of the Guidance, Navigation, and Controls Lab at the Kent Space Center. And then this lab and the whole building was damaged in the 2001 earthquake and later demolished. And that's why I can show you the pictures in that. Otherwise, they would not allow it. Again, that email doesn't work. It's mike.gamble.retired@gmail. Okay, this is a picture of the facilities. It sets down in the Kent Valley there. You got Mount Rainier in the background. The big tall building here is the 24 building that was built because it has a chamber in there for testing. Boeing built the first stage of the Saturn rocket, the moon rocket, and it's 80 feet tall. It's for testing the acoustic vibration. And then my lab over here is in the 21 and 22 buildings off to the side, is where I was located at. Okay, we'll start with gyro principles. Basic principles of a gyroscope. There are three orthogonal vectors. You have the spin vector, which in this case is highlighted in red. You have the input torquer vector, which is highlighted in green. And you got the output vector, which is highlighted in blue. And the way it works is there's three contributing factors. You have the mass of the rotor, the speed it's turning, and the speed of the torquer. And those three contribute to the output vector's value. Now, this is a simple little demo model that we had floating around the lab there. There's two gyroscopes side by side, and then there's a figure-8 belt that drives them. So they, we call it scissoring. The technical term is differential operation. But the key point is you see the green vector here, which is the torquer vectors, are in the opposite directions. The end result is the two output vectors are in the same direction. So they twist sideways, one clockwise, one counterclockwise. They're spinning the same speed and they have the same mass on the rotors. Okay, now the way this works is the faster you torque them, the higher the output. So you want to torque them fast to get a big pulse, and then on reset, which is this time here, where you're going the opposite direction, you want to torque them real slow so you don't get much negative pulse. So when you average out the big positive pulses with the little negative pulses, you get a positive average force. And that's the theory behind your scissoring or differential gyro operation. And now we'll talk about the different types of gyros that I played with there at Boeing. This is a little bit different than the one I just showed you. It has two similar gyros with a figure-8 band, so it does the differential operation there. This one is a little bit different. It's called a reaction wheel. You just start it up or stop it whenever you need force. It's about an 8-inch wheel. The next picture here shows the exploded view of it. The rotor is about 8 inches. Then you got a permanent magnet rotor here for the driving. And then it sits in a vacuum can. You got face plate, bottom plate, side plate, and then electronics that drive it. This is a little bit bigger gyro that we ran. The gyro sits in a vacuum can here, and you got the motor over here and the servo or position sensor over here. And then you got one gimbals here, so you have control over it. Now this is the big boys that I played with. They're big Sperry gyros. You have the blue torquer motor over here, and then the position sensor over here. Now the rotor is 24-inch rotor in the vacuum can here, and then we put a plexiglass shield over there because you can pinch your fingers in the gimbals. And then we got the power electronics down here. And side note on that is my boss told me to take very good care of them, as they were worth far more than I was. They're about $1 million a pop. And then we'll give you a little tour of the lab facilities. Like I said, it was built in the 60s. We had a space simulator room. We called it the black room because it was painted flat black. But the key component in there was a 20 by 20 reinforced concrete slab, which was about 70,000 pounds. It floated on 24-inch air cylinders. There was 7 of them under the pad. So it was totally isolated down to the micro-G range. In the center of the pad was a 4-foot pedestal with a bowling ball type apparatus. So we floated the mechanism on that. Of course, there was tin over the gap here when we put it all together. Now, when the earthquake hit, myself and another engineer were actually standing on this pad, and it worked perfectly. We didn't feel a thing. The ground was going up and down, and it stayed perfectly level. What got my attention was the overhead crane started dancing, and I knew we had a problem. This is outside the control room. This door here goes into it. When it was running, nobody was allowed in there because it was too dangerous. But we had this little peephole over here where when you looked in there, it was just like looking into space. You could see the satellite or the test article, and then there were star patterns that we put in there and a sun simulator. The only thing we couldn't control is vacuum. The chamber itself was EMI, thermal, optical, and acoustical shielded, but vacuum we couldn't do anything with, so there was always a little air drag. Looking over at the control console here, on the left you had the air bearing controls that floated the pad. The center controls were for the air that ran the float for the test article. And then the right hand was the controls for the test article itself. And then if we needed to generate magnetic fields, we had a huge set of 3-dimensional Helmholtz coils that we could put around the test article for generating any type of magnetic fields. This next one here shows a picture of the sun simulator. It was a hexagonal honeycomb structure with a light bulb in each honeycomb. Each honeycomb was about 4 inches or so around, and then you could move the lights in and out. The whole structure would go in and out for focusing, and then the lights were dimmable, so you could simulate the sun at thousands of miles out into space. There was also the star pattern lights, but I couldn't find any pictures of them. We would hang these little light bulbs in a star pattern, like let's say you were looking for the pole star, you'd see a little dipper in there. They were similar to the little light bright toys that kids use, only industrial strength. Looking into the control room here, this is late 60s, early 70s. And as you can see, all data was collected on strip chart recorders. You won't see a digital PC in there anyplace. The guy over here is playing with an analog computer, but no digital PCs. The test article itself, this was the sun sensor. It was actually 4 sensors, and then the computer would take differential readings to determine where the sun was, and it would track that. And then we had the star tracker, which would track the star patterns we were going for, depending on where you put them. But the object of the game was it would track the star pattern and the sun, and then it would control the gyros, which supplied the force. You'd get this thing spinning, and then it would have to stabilize itself and lock onto the star pattern or the sun pattern, whatever you told it to, and stabilize because it was a simulated satellite in space. Don't everybody laugh at the computer. 16 bits address, 8 bits data. You could replace the whole kit and caboodle with a laptop, and it would be far lighter. Now I'll show some of the test articles. This was an early CMG. The little cone-shaped area here is where the bowling ball rode. You can see one gyro here. There was about 4 of them spaced around there. If you judge by the guy's white shirt, narrow tie, and a 260 Simpson, that would put it at early 60s. Okay, this shows it on the pedestal. There you can see the bowling ball. There was high pressure nitrogen comes up through this hose. There's a whole bunch of little holes in this bowling ball. It was about the same size as a bowling ball, only it was made out of steel. I think it was stainless. Weighed about 100 pounds. And it floated, the test article, very similar to an air hockey table. This picture shows the dynamics of it in time-lapse photography of the range of movement of the test article. Also, the gimbal was locked here, but it was capable of spinning also. Okay, this was another one that we tried. Here you see the triangular base and the bowling ball that it floats on. There was 2 medium gyros out here, and then it was counterbalanced by the battery pack and the electronics. Gal in the mini skirt there would probably put it at late 60s. Okay, this was a measuring the range of motion, pretty crude, protractor and pointer for roll and pitch. And here again is a picture of the test article with the 3 gyros, the medium size on both ends. And then you got the battery pack and electronics. And there's, you can see the wires. We ran up to a swivel up in the ceiling. You just get a small view of the crane there that lifted it. The test article is about 1,500 pounds. This is a view of the other side. You can see the wires going up to the ceiling there. And same thing, looking at this guy here, he's now got a colored shirt and lamb chop. So you're looking at about early 70s. Moving on here. Okay, this shows the other side. Here's the 3 medium gyros over here. Now the picture's colored, so we're now getting into late 70s. There's a better picture of the overhead crane. That's the one that started dancing and when I got concerned. And then there's your cables going up to the swivel in the ceiling for this thing. This particular one has a antenna dish on there and counterweights. What we tried to do was simulate satellites mainly out at GeoSync because we did a lot of work with them. Like I said, we calibrated the flight controllers also for taking them out there. Now this particular one is the one that I actually worked on. We used to call it old bug eyes because if you looked at it from the front, it looked like the head of a fly with the big bulging eyes. Now, if you look at the floor, you'll see a whole bunch of scratch marks in there because this thing didn't always do what it was supposed to. Excuse me. Gotta take a swig here. Talking too much. Anyway, I used to tell the boss if you put a saddle up on top, it would beat any mechanical bull in town. However, nobody's allowed in there when it was running because it's just too dangerous. This is a rear view of it. It also shows the sun simulator over here and the 2 bottom gyros on it. And then one of the tests we did with it was what they called station keeping. When this thing is parked out at GeoSync, the antenna or whatever electronics you have that are supposed to be pointing at a particular point on Earth, no matter what the gyros and the stability and the orientation of the device. Okay, this is the side view. What we simulated that with was a balance beam. Put this big balance beam up on top, and then we had this big, it was built out of PVC pipe, and then we tensioned it with turnbuckles. So as we changed the orientation of the rig here, the balance beam had to stay exact. It was not allowed to move. That was the test. There it shows a lot more of the scratch marks on the floor also. And then this picture here was the end of the game. These 2 buildings are now demolished. Amazon.com has a warehouse sitting right where my lab used to be. This door on this wall was a center transportation aisle down the center of the building. I had this corner over here. Oops. And that's the end of the show. All that data is useless because I'm retired now. So anyway, that's the quick pitch on Boeing gyroscopes. Like I said, it started in the 60s. And I got in on it about 1995, just when everything was starting to slow down. And then we hit that 2000 earthquake, and that finished the gyro work at Boeing. They scrapped the lab, and the whole building is tore down. So that's the story there. I guess we're ready for questions now for whatever you want to ask.
Wonderful. Well, Mike, let me stop sharing there. And again, and since you're not going back in, we should be safe. I'm going to put it on screen view. I'm not going to unmute everybody, but again, another giant hand. That was amazing. Historical photos, historical